What if a vision transformer could spend more compute on hard images and less on easy ones, without retraining and without a separate router? That's ThinkingViT. I'm Yannick Haberer, and this is a joint work with Ali Hojjad, Sören Pirk, and Olaf Landsiedel. And now, let me show you how it works. So, let's start with a simple example. We have two images, one of a sea turtle and one of a duck. And, well, these images are very easy to classify. And we don't have to think long to really figure this out. Now, if you look at a few more examples, it gets a bit more difficult. So here we have a bunch of muffins and chihuahuas, and they kind of look a lot alike. So yeah, you have to think a bit longer to figure out which one is which. And if you now think about how vision transformers work, they can't really do this. They will always spend the same amount of compute on every single image, whether that's the sea turtle or the duck, or whether it's like such an image which is a bit more difficult to classify. And that means that we are wasting compute on easy samples while maybe not spending enough compute on harder samples. Okay, so let's see how ThinkingViT actually works. So we start very normal. We just extract our patch tokens from the input image. But then we do a lightweight inference pass. And that is possible because we use a nested transformer. And this allows us to run the network at, for example, half of the capacity. So we can use half of the attention heads and half of the neurons in the MLP. Could be also less, could be more. We then make a prediction, and then we check the entropy of the prediction, so to check the confidence of this. If the confidence is high, then the model just stops and outputs the prediction, which means we didn't spend a lot of compute on what is most likely an easy image. If, however, the confidence is low, so we are not really sure with our prediction, that means the image needs more thinking. And therefore, ThinkingViT will rethink the input with more model capacity. For that, it recycles the tokens that were produced in the first round. It will use a projection to align the dimension mismatch, and then fuse the produced tokens back to the original input using a scaling factor. And then it will finally run the model again using more attention heads. Now, this could be the entire model, but this could also be another intermediate step. In case of an intermediate step, we would then do another confidence calculation and see if we are now confident enough. And then if we are finally confident enough, or it is already using the full model, then we output the final prediction. Okay, now let's take a quick look at some results. So here we trained ThinkingViT based on a DIT small architecture on ImageNet 1K. And in this plot, on the x-axis, we have the Gmax. On the y-axis, we have the top 1 accuracy. And what we can see is that in the Gmax range of ThinkingViT, we outperform every single nested baseline, as well as the standalone DIT tiny and DIT small models. While some of the models are achieving a slightly higher accuracy, they need way more Gmax to achieve that. And it doesn't stop there. ThinkingViT can also be applied on top of models such as Swin Transformer. And here we see that we match the accuracy of Swin base while needing only around half of the Gmax. And we also beat Swin small and Swin tiny with just one single model. And finally, we show that ThinkingViT remains a suitable backbone for semantic segmentation, just like your vanilla vision transformer or DIT. And we do this by using ThinkingViT as a segmenter backbone. And in these two examples, you can see that after the first round of thinking, the segmentation is quite noisy and not really that clear. Whereas after the second round of thinking, the result is much improved. So we can see a nice segmentation and it's much clearer. So that's ThinkingViT, which brings input adaptiveness to nested vision transformers. We do this via multi-round inference, where ThinkingViT activates additional attention heads combined with reusing produced token features to achieve better efficiency. For more details, please refer to our paper or visit our GitHub repository linked below. Thanks for watching.